but it was very nice to that we invited. Thanks for visiting. An old and some of the concepts finite-dimensional or norms or convergences. So the show you that the Heisenberg group also appears in a different setting way, not connected to any kind of applications. Namely, when you have to solve a basic problem in geometry, namely you want to construct vector bundles over most important non-commutative manifold, namely the non-commutative torus. And then thanks to Mark Riefel from Berkeley, the way to do this is to construct Gabor frames. He showed that if you put them in this perspective of non-commutative geometry, you really are vector bundles over. And so there's a lot of theory that people have what people time frequently think about. But the nice thing is, in the end of the day, this descriptions of this vector bundle have really a lot of control over them. Usually have like, oh, there exists some generators, but they have like, look, this is useful to tell them. It works for some values and for others not, but for example, totally positive function type. This is nothing. It's very them. So the point is now that the reason why I really came up with this to this in there too. So you have to have Gabor frames over this fine to get. So yeah. So I don't know the Ron duality. Any here at this workshop in January where Ron duality was discussed, but in selling this relation between geometry and time frequency, and it really explains why you have a dual description of your. At the end of the day, that two non-commutative spaces are the same, and this means that they're more that is same. And so yeah, so I guess I will start with the Gabor frame case, Gabor type case. So and there's no reason for what GB. Then you N, and then you can associate to it its characters, G hat. So again, a finite abelian group, the same cardinality. And using the basic things in homomorphisms, you can do two things. You can and this you build this type of shift, so you have you do this cyclic shift and you do modulation. These two you build time frequency shifts. Pi, KL, which are M1 to the L, T1 to the K. And as mentioned, these two don't compute, so you end up only getting a projective representation. G cross G hat, so you have this mapping from KL to your time frequency shifts. And in other words, you have that T1. Because you have the T1 M1 is e to the 2 pi I. M1 T1. You get this relation that we had in Peter's talk, that pi of KL, pi of K prime, L prime, is equal to this phase vector that's built out the collective form. So this is the symplectic form. Of these 2 points in G cross G hat. So if you have to deal with commutation relations or whatsoever, you always have to keep track of this. And we also want to this also has other consequences, namely if you want to look at the sum of also that this phase vector comes up, so you have pi of L, K plus K1 plus K1 plus L2. Then it's pi of K1 L1, pi of K2 L2, and some extra phase vector that keeps track of this one here. So this is equal to pi I, most likely minus, I think, L1, K2. And so, in general, this is known as a 2 co-cycle. And this describes your representation. And so this one is just C. Yeah, usually we'll denote this by C of K1, L1, K2, L2. So if you take a complex conjugate of this and the other one and multiply it with this one, then you get the symplectic form.
So just again, refresh memory of
Yes. Yes. There is here.
So G cross G hat is Euclidean, and the map is a non-Abelian group, from onto a non-Abelian group, but the non-Abelianness is only inside the base factor, and that makes the projective representation, right?
Yeah. So this is one way of keeping track of your I mean, here you stick it inside your different group, then it's in there when you look at the factors, or you write it explicitly and keep track of it while you work with representation. If you have a representation multiplied by factor and you ask when is the representation again, this is the condition to satisfy the associativity condition. That's because it satisfies this G1 of G1, G2, comma G3 equals to G1, G1, G3, this condition. But but the point is, as always made, this phase vector is important, so you can't ignore it. And so if you take all the points from your phase space or time frequency plane, or if you take all the points, yeah. So if you look at it as describing your representing your, then it's irreducible. And so it means that we can write every function or signal as 1 over melody of G. Oh, maybe KL F for any G. And this is the matrix coefficient of your representation. It's also known as the short time Fourier transform or a sliding window transform or whatever. And usually I will denote it by VGF of KL. So the information that you get from your matrix coefficients enough to represent all your signals. The situation changes if you restrict your interest to just as points from sub in your plane. So this is our before. Then you have to be more careful with picking. Yeah, I should have said that it's L2 norm of this is 1. Otherwise, you get some norm effect. If you would like to do the same thing for restricting to subgroup, it's a little more challenging. You can't randomly think, and you also have to usually you have to settle for picking a g here and then other function here. So then it's much easier to find if you would like to stick to the tight frame case. So what you end up with is, if you denote so we restrict this to this subgroup case. And so the question then becomes when is this operator invertible, or this is H. So the question then so you want the problem becomes that this is the identity, and usually it's phrased in a way, namely that the frame operator which you can write it as inverse, or as inverse as, and that this is a nice self-defined operator. And the condition that you, in other words, if you put explicitly the condition that you have a frame, a Gauss frame, means that there are constants A and B such that A should hold for all lambda for all f, and this is equivalent to say this operator. So I didn't talk about the bound distribution. The crucial point is that you get this lower bound. To talk about, there is a way of writing the frame operator. There's another description. Namely, given the structure that this operator has, marginal operators, that with your frequency from this lattice. And this hint might be useful to look at in the phase space for which commute with pi. So, or not in this setting, it merely means to look at the commutant of the set of operators that you look at. So you have this family of operators pi of lambda. in the case where you took the whole phase space, the only thing you get if you look at with those is multiples of the identity. So this is one reason why you have this representation. So you look at the operator commuting with those. And given what I said at the beginning was, if you relate to you have to get this vector, so if you want to commute, this has to be so points KL G cross G hat such that pi KL commute for all lambda and lambda. And this is called the adjoint lattice. And turns out that because this operator, this SGH, has this very particular structure, you can actually express it in the following form. So if you look at it on the edge in this edge, sure, you see that f and h have changed places, and obviously you only have to you take the inner products between the functions that you're interested in, the function that should be dual to the and the function that you started with, and is decoupled from your system that you look at. So, in other words, you might wonder at the structure of those operators of this form, and these this is the link that also have to understand the quality of the canonical dual or canonical type. Your G has a certain quality, so in the continuous case, if your G has a certain quality that you know of, and you might wonder if you can find nice H's, so like for example, that because you have this commutation relations of this invariant frame operator, you always end up that your dual atoms that you construct are only depending on s minus 1 G and s minus 1 half G, and it turns out tides are also way to see this because the element in case, so in the function case it makes sense to look at it. So what this should motivate is these elements. A of lambda, pi of lambda, or not. These are elements of this famous torus algebra. We have these so you can, in the finite dimensional case, there's no problem. You can multiply them. You can an element of the same type. So you get some nice involutive star algebras. But so if you would this representation, then get here for the product the convolution of the sequences, and you would have just taken a lambda bar. But since we have this twist, this cocycle, you get only twisted and let's keep track that our system from twisted group algebras. And let's denote them by a lambda naught. A lambda c. And to explain the rest in the part of the talk is the following, is the statement that raised it. Yeah, that is two ways of writing the framework is equivalent to saying that these two algebras are Morita equivalent. So So this also holds true in general. So if you for back to B group and the letters in, and this is a theorem by Weyl from 1988. So the paper has the title "Projective Model," and in establishing this Morita equivalence, he figured out that the way to do it is to construct Gabel frames. That's what we are going for. End of the talk. So the point is that, so I will not try to explain you that why these, so these are so-called non-commutative tori. Why it makes sense to talk about non-commutative spaces, and notion to say when two non-commutative spaces are the same turns out that this is the one that's more important, the right one. Morita equivalent. Just this to more relations, rigorous to restrictive. And then Morita equivalent in C star was said was introduced by the 70s, and so you will finite dimensional setting, this amounts to checking this relation that I've written down, which is not straightforward. I mean, you would not guess that you might have some perspectives. So, Kohn in the 70s, early 80s, he theorems for the classical ones didn't work. So when you had quotients, if you have the quotient out and you get something singular, would like to be able to handle this with the traditional theory, or like get similar results. So in this attempt to came up with his proposal to talk about non-commutative spaces, and not even just non-commutative spaces, but do some geometry on them. So he then tried to formalize notions in terms of which don't care if your algebra is commutative or not. And it's all based on this old field of Gelfand and Naimark. When did it start? Okay. Good. So this theorem of Gelfand and Naimark is that commutative C-star algebras are all of the form let's put unit of in here, make our life easier. C of x for some compact Hausdorff space, namely so this is the space of maximal ideals. Together with the weak star topology. And okay, C-star algebra just means you have a nice involutive star algebra with a norm which respects your algebra. And it's also complete. So if you have those properties, you would say it's an involutive algebra. But now you have this extra property of A star equals the norm of A squared. So if you take the, and here I always equip it with the sup norm. So if you take here the continuous function, then this is satisfied, and your solution is going to taking the complex adjoint. And the other prototype of this thing, forget about commutativity, is the bounded operators in a relevance space, and then the operator norm satisfies this. The big theorem of Gelfand. All these algebras, it doesn't matter if it's a commutative or not, can be on the Hilbert space of bounded operators. So since this, in the case of commutative C-star algebras, you you get this canonical object associated to it, this compact Hausdorff space. For okay, if we draw commutative and get some C-star algebra, we still want to think of it as some continuous functions on space, and this is this new space. So, and it was one motivation of Kohn to understand basic properties of quantum and Weyl commutation and basic structure of the phase space that comes through the non-commutativity. Oh yeah, I should do this. Wait. You're really glad to look at just that C-star algebras that are by operators, but by unitary actually that satisfy the commutation relations of pi. Unitary operators. So unitary operators satisfy the commutation relation. So if you have two unitaries, VU equals to pi I theta V UE. And you look at the C-star. This is called for this value theta. And of course, if theta is 0, then there's no non-commutative torus, and then you can show that take the multiplication by e to the 2 pi I psi, both components of your torus, that both circles, that this is the, so that for A0 you get continuous functions on the torus, and if theta is yeah same thing. Simple for matrix out perhaps a vector bundle rank n or when theta is p over q. So one way, as these come in very different flavors, and if I have time, I will talk about it. So you yes. You look at the C-star algebra, you like the more the idea to get some concrete objects and to understand what objects value. The space algebra. yeah, if you take lambda, also if this is e to the 2 pi I over n, then that we talked about before. But the point now you associate it to this. You want to think of these algebras as living on a torus, and this relationship you have between those objects tell you that these two are identically dual to each other. So this is the same kind of stuff. And what the Gantt then did was he took a theorem of Swan that vector bundles over the continuous functions on your compact Hausdorff space are the same as finally generated projective CFX modules. This into a definition set vector bundle over a space, let's call it A, noncommutative C-star algebra is just a finally generated module. Then you actually want to extract that this vector bundles in the classical case structure actually like given by Hessian is given by the Hilbert C-star module structure on this algebra. This means you have product takes values in the C-star algebra. Standard one, but the complexity becomes star operation and activity means activity of the operator. So you have and scalar multiplication means that you have an action of your module of your algebra on your module. Yeah, these are the most, yeah. And you have another space, another C-star algebra with another module. So with the structure from a right module like this. So then you have on A. This is the only difference. And then you if you have structures that are compatible. I'm running out of time. Yes. But still, the structure. If you Yes, yes, but why the comes up here is if you want to equip your finite algebra, your matrix subalgebra with a Hermitian structure, you want to know when does it give rise. It's not that every other that from the element let it. So
I got to also essentially we have it in a table. So we need to I think we don't want to rush anybody, but I somewhat got like the way we started the vector ones, I got a bit lost.
yeah.
Somehow I don't know if you don't know,
But
if you can somehow wrap it up and
yes. So that this will take for you have a left and right model structure and inner product, and if you're able to show that these inner products satisfy this associative, you see. And now examples of this inner product. So in our case, if you take this lambda, then this is f pi of lambda g f lambda. This defines that satisfies these properties. And the action is really you let this pi of lambda act on something. So this versus operates as SGH. Because this module is a rank 1 module. So the Galois frame type operators are rank module for this module. And the second part really is if you take for this inner product the one that comes from the edge of lattice. And for checking that this is satisfied, it has to check this representation. Your frame operator in two ways. It's the same thing. This shows that lambda and in with noncommutative geometry. Just say Morita equivalence in the algebraic sense, then it's free. But if you want to have this inner product or some inner product, no matter what is get exactly those finite-dimensional versions. And the reason why Luef was interested in this whole thing was, so he had up the question, how in thought that that's the case for lattices in R2. So in R2, these are times finite. This theory of function topological. like decay theory. But he never was really interested in this stuff. Never explicit Gauss. In his theory, you just get the existence of some motive in the Gauss frame, and this is enough for some nice. He never explicit one. But problems you need, people are like looking for explicit constructions and even how the proper way that really keeps track of the inner products. Okay, thanks. He had the whole thing. Yes, he realized you can use the restriction of the Schrödinger representation to a subgroup, to this lattice, to these factors, to satisfy this condition. So no, it's simplified in the sense that you really what that you can so you could also define the can write make this simplify still involves this GIs.